All right, so hello and welcome to Algorithms Live. And this week's episode is going to be on this thing I'm calling Biconnected decompositions. Really, the focus of this episode is basically a continuation of last week. Last week, we learned about DFS low linking, how to extract all these components, two vertex connected, two edge connected components from graphs. We learned what cut, vertices, and edges are. And so what we're going to learn in this episode is how to turn these into trees. So different methods for doing that. And it's going to be kind of problem driven. I've got a few kind of unique, interesting problems that I think are really good examples of how to use some of these ideas. And there's even more in the blog. So if you go look at the blog post, you can solve even more problems related to this. So the first problem we're going to look at is actually a problem not in the blog, but I think it's kind of useful. And I'm sure this problem exists somewhere in some form. I think there's an old AMPPZ problem, but I couldn't find it. But if someone wants to drop in the comment, I'll add it to the blog post as well. But basically, the problem goes like this. You're given some kind of graph. And so it's just an undirected graph. It can be any kind of undirected graph. Just drawing a little bit of an arbitrary graph here. And the way the problem works is we want to add edges to the graph. And we want the minimum number of edges to be added to the graph such that there's no more bridges in the graph. So if you look at the graph right now, these are bridges. You cut these, the graph ends up becoming disconnected. You cut any of those. And so what we'd like to do is essentially we're just making the graph two edge connected by adding the minimum number of edges. And so that's part one, is just like find the minimum number of edges to add. And the second problem is report the edges. So that's the problem we want to add. So for this sample graph, I could potentially add an edge here and potentially add an edge here. So the answer would just be two edges. I don't need to add any more edges than that. And now I've gotten rid of all my bridges, as you can see. So that's the problem. It looks a little bit complicated right now. So the first thing I'm going to do to try to make this a little simpler is you'll notice that anything that is a two connected component, so if I draw a two connected component like this, doesn't have a bridge in it, pretty much by definition. And what I want to do is I just want to ignore those pieces of this problem, and I'll simplify the problem a little bit. So what we're going to do is we're going to take the two edge connected components that we have so far, and we're going to apply a transformation on this graph to form a metagraph. So a metagraph is a graph that represents some piece of the original graph, but it's often simplified in some way. So here's our transformation. So here's the original graph, and what we're going to get out is a tree. So here's how this is going to work. We take the two edge connected components wherever they exist, and we turn them into nodes in the new tree. And we also take all the bridges or cut edges, and those become new edges in our tree. So if I take the graph I have up here, so maybe I won't redraw it, I'll just copy it. Something like that. You get rid of some of the edges. If you recall, the two edge connected components are just vertex sets. So it's these four vertices here, these three vertices here, these four vertices here, these four vertices here. What I can do is I can just run a normal BFS multiple times, ignoring crossing any bridge. So just label the bridge with a bridge ID. Don't go over it if it's a bridge. You'll notice this becomes a tree. So I do a transformation like that, and those little blue circles become nodes entirely in my new tree, and I hook them up like this. And so you just hook them up if there's a bridge between the two connected components. So that's where these bridges kind of pair up like so. So pretty straightforward. And so that's the first transformation. So what's nice about this is now if I'm doing my problem in terms of like pairing things off, I only have to solve this problem on a tree. I don't have to solve it on the general graph, which makes it a little easier to think about. Often problems on trees tend to be a bit simpler. So that's my thinking anyway. Okay, so how do we solve this problem? So now the version of the problem we'd like to solve is, given a tree, what's the minimum number of edges to remove all the bridges? What's the minimum number of edges I need to add? Okay, so we start thinking in terms of the tree, something like this. And I'm going to draw it kind of like a rooted tree here. One of the things you'll notice is these things down here, they're called pendant nodes. So any node with degree 1 is a pendant node, or sometimes you'll think of it as a leaf if it's a rooted tree, but I'll use the word pendant node. And so we have 3 pendant nodes right here. We can see that if we don't hook something up to a pendant node, if we hook it up a bit higher, then this edge doesn't get covered, but anything that could have been covered right here also could be covered if I hooked it up one back. So it's a really informal argument, but basically the idea is there's no point in excluding this edge extra. So in order to cover this edge, something has to be on the pendant node in order to include this edge at any point, or to make it not a bridge is the best way of putting that. So I can pair off pendant nodes, basically. And then the other edges will mysteriously, through some unseen process, potentially get covered. But the important thing here is we know we need at least that many edges. We might need more, but we know that this is at least necessary number of edges to add to be our solution. So it ends up being P divided by 2 ceiling. Number of edges to add. So in this case, there were 3. So 3 divided by 2, the ceiling of that is 2. If there was an extra node here, I could do it with just 2. I could add this edge here, and I could get it that way. But I can't do it in 1. That's also 2. And so if you play around with this a bit, you'll see that in most cases you can actually, or actually in all cases, this is also sufficient. So what you could play around with this and you can think, okay, what's the minimum number of edges to do? It's always just going to be the number of pendant nodes divided by 2 ceiling. So that's always the answer. But this could be a little bit weird to think about, because we kind of have to prove that that's the case. And if we're doing the construction, we want to come up with a way of adding edges to this tree that's actually going to get us the connections. So it's fairly easy to hook things up wrong. So if I hook up these edges here, one here, you'll notice that these are still bridges. So we have to be a little bit careful how we're hooking up our pendant nodes, because just hooking them up and pairing them up any old way doesn't necessarily solve our problems. So we need to do a little bit better here. So we want to do stuff with these pairings. Important thing to notice is if we connect things in different subtrees, then everything from that node to the root ends up getting covered. That edge ends up getting covered or removed as being a bridge. That's one thing you'll notice in terms of this. So if we make everything leave its subtree, in other words, like all the pendant nodes coming from each side, if this one leaves its subtree, so here's the subtree here, here's the subtree here, and this one also leaves its subtree, then we're good. We could draw a more complicated graph. Something like that. So I could hook it up like this, have everything leave its subtree, and then we're also good in this case. So that'd be good. So we want to pair things up. There's actually a bit of a problem here, though, with pairing things up. Let's say we root the tree like this. Well, now if this is the rooted tree, here's the subtree. Here's the subtree over here. If we pair things between the pendant, like we can't pair them up here without using n divided by 2 ceiling pairings. This is kind of a problem. So you can see that that's actually an issue. So we can actually rework this problem a little bit here. One of the things I want you to consider is something called the pendant centroid. That's just a name I'm making up, but I'm going to call it the pendant centroid. And so what I mean by that, it's a node where if you select that node and then remove it, the number of remaining pendant nodes is as small as possible. Like you divide them up as much as possible. So for example, in this tree, if I want to reroot it, I would actually pick right here because the subtrees that remain, that's a size 3, and a size 1 subtree that exists. So I could reroot the tree this way, come over here, and get something like this. And now everything's divided a little more evenly. Kind of a neat thing about finding this pendant centroid. So what you could do is it's just like finding a regular centroid, but instead of storing the subtree sizes, you store the number of pendant nodes in that subtree. So nodes with degree 1. And you can find it just as easily that way. But the important thing is each subtree, this number of nodes in the subtree is always going to be less than or equal to the number of nodes in the tree divided by 2 floor, the number of pendant nodes. So you're always going to at least divide it in half, which means that there's always going to be a pairing that exists that doesn't leave the subtree, that ends up getting out of the subtree if it's rooted at the centroid. So that's kind of a nice thing in terms of pairing subtrees. Now we don't have to worry about this case. We can just make sure that these are paired, these are paired, these are paired, and maybe these are paired. And so every edge here has left the subtree, and then everything is fine. So that's one way we could think about that. So how do we want to do the pairings? Well, now that we've got our pendant centroid, what I could do is I could do an algorithm like this. So imagine that this has 2 pendant nodes in its subtree. And imagine that, and so here's my centroid. Imagine that this has 3, and imagine that this has 5. Okay. What I could do is I could do a sort of algorithm where I just keep them sorted in a way. So maybe they're like 8 in some subtree, 7, 5, 4, and 2. And what I could do is just greedily pair the 2 subtrees that are at the front, remove them, and then knock them down by 1. So this becomes 7, this becomes 6, and then continue the algorithm. So the easiest way to do that is you don't actually have to keep the full sorting. You could use a priority queue. And the running time of this algorithm would be O of p log p, where p is the number of pendant nodes in the tree total. So that's pretty good. And I won't prove this greedy, but it actually works. If you always just pair in this fashion, you're always going to level things off fairly evenly. You'll pair things in different subtrees, and you'll get rid of all the you'll get rid of all the bridges in this fashion. We can actually do something a lot simpler. And so that's what I want to talk about, because I think the simpler version is cool. And so I definitely think it's worth talking about here. So one neat way of thinking about trees is through their tree traversals. I'm pretty big on tree traversals. They're just useful in general. So if I have a tree like this, you can look at the tree traversals going down, up, down, up, down, up, down, up, something like this. I don't lift the pen. And so what you'll notice about this tree traversal, sometimes this is called the Euler tour of the tree. This is actually the idea that Euler tour trees are based off of. So if you've heard about that data structure, it's basically just this idea of not lifting your pen, doing a tree traversal, and saving numbers based on where that occurs. Probably cover that in a future episode. But one cool thing about this is notice that when you're doing a tree traversal, the subtrees get grouped together. You always process a subtree before you process any other subtree. So this subtree is all processed together. It's got a tight Euler path between it. This one's all processed together. And what's cool about this, in my opinion, is this lumping of subtrees is invariant wherever you put the root. So if you reroute the tree somewhere else, so if I reroute it over here, then all of these subtrees are going to be together in terms of that Euler tour path, going like this. Okay? So just think about that mentally. Think about rotating this tree, but then the relative order of this traversal ends up being the same. And you can just follow that blue path from this root node. Just cut this. It's basically a cycle. So just cut this, or closed circuit. Cut this closed circuit around. And you'll just see everything still gets grouped together. So what's really cool about this, you can take the tree rooted anywhere. So imagine it's not rooted at the tree centroid, and that's certainly the case here. What I could do is I can go through the pendants in order and label them based on when they come up in the Euler tour of the tree, or the tree traversal. Something like that. Okay, so here's the second thing. We know that the centroid of the tree exists, and we know that these pendants are in the same relative order as they would be as any other tree traversal at a different root. So in other words, if we take a node and always hook it up to the number of total pendants divided by 2, if I take the floor of that, if I go this far away, then I'm always leaving my subtree relative to the pendant centroid. So here's how I hook things up. In this case, it's 6 divided by 2, so that's 3. So I'm going to hook things up that are 3 away. These are 3 away. These are 3 away. These are 3 away. I get rid of all my bridges that way. So all I have to do to solve this problem, I don't have to go through all that effort to find that pendant centroid. I just have to know it exists. And I have to know it divides each of those subtrees up into PT divided by 2 subtrees. So I think that's pretty cool. So I know that those things exist. I end up leaving the subtree just by hooking the first pendant node up to the 4th one, the second pendant node up to the 5th one, the third pendant node up to the 6th one, and so on. And that's all I have to do. So to end up solving this problem fully, all I have to do is decompose the graph into 2 edge-connected components, turns it into this tree, run a DFS on the metagraph, which is this tree, which I could build using what we said, and get an ordering on the pendant nodes, and then just hook them up this far away from each other, and I'm guaranteed to leave my subtree. And it'll always get me my answer, which my answer was P divided by 2 ceiling number of edges. So if you need the construction, that's all you do, and on a general graph. So that's our first problem. It's surprisingly not as hard to code as it sounds, but it's kind of a neat idea. Okay, so let's talk about the second problem. The second problem is an ICPC World Finals problem that I really like, and it's called Minding Your Own Business. Okay, so here's the way this problem works. What we have here is a graph, like so. Add a little bit more. And what we have, the edges are called tunnels, and the nodes are junctions between the tunnels. So you can think of it as we have minors in these tunnels. So the tunnels are the edges. So there's minors here, maybe some minors here. They're all just dispersed out through the tunnels of the graph. And what we'd like to do is we'd like to drill escape tunnels. So in the graph somewhere, so that if one of the junctions goes out, if there's a collapse in the junction, so maybe there's a collapse right here, then all the minors can still escape. They can always get to an escape shaft. So what we'd like to do is we want to drill these tunnels. So we want the min number of tunnels to drill. So escape tunnels to the surface. Like minimum number of escape tunnels to the surface. And we want, if one junction goes out, then the minors can still get to the surface. So we want to count that. And then we also want to count the number of solutions. So it's also a counting problem. Okay. So how do we solve this? So the first thing to realize is if a cut vertex collapses, then the graph gets separated. So if the graph doesn't get disconnected, we can always get out. So let's say something that's not a cut vertex collapses, then everything is okay because we can just get to any other node. And as long as we have at least one escape tunnel, then we're fine if that one collapses. But if anything else collapses, but if a cut vertex collapses, then we're kind of in trouble. So maybe that node collapses. Then all of these guys, with the way I drew these escape tunnels, could escape out this tunnel. And all of these guys could get out through this tunnel. So we're looking pretty good so far with the tunnels that we drew. So this problem is still pretty complicated, though. And so what I want to do is I want to use a tree decomposition, if I can, or some kind of graph decomposition of my two vertex connected graph to make it easier to solve this problem. The observation here is if I'm in any component that is two vertex connected. Notice we are dealing with articulation points, so that kind of tipped us off that we want to use the two vertex connected components. If anything in that component collapses, we can still get to everything else in the component. So if I collapse that vertex, I can still get from any edge to any other edge, can get to one of these nodes. So decomposing the graph into two vertex connected is a good idea. So if I have a two vertex connected graph, I'd like to turn it into some kind of decomposition. And let's see if we can get a tree out of this, because tree would be the most useful thing. So let's take a look at our first decomposition. So maybe this is the graph we're given. So a decomposition you might try is, remember, the two vertex connected components are an edge set. So that's one, and I guess I can draw the other one here. It's these edges and these edges. So if I do something like that and I move it over here, I get one red edge, one blue edge, and I'll hook them up with white edge between it. And so I get a graph kind of like that. So it's this component mixed with this component. And we look at that, and it's a tree. So it looks like a tree so far. I could also draw a different kind of graph. This graph is going to be a little bit more problematic, though. Actually, drawing a hazard sign is like caution, radioactive or something. And if I do something like that, these edges right here are one component, these edges right here are one component, these edges right here are one component. So I make those sets of edges nodes. And I want to draw edges if a component here touches another component over here. Well, then I get something like this. And that's not a tree. And the thing you realize about this is you can actually just like add more of these size 3 cycles. And what you'll get is a click. So this is even potentially a click, which is really bad because that's a lot more dense than the original graph. We want our decomposition to actually be simpler, and now it's getting more complex. So this is not a good transformation of always just hooking them up like so. And what we want is we want a tree. So none of these really meet that criteria. So we need to get around this problem of turning two vertex connected components into trees, because trees are simpler and also more useful. So here's the idea. So the solution to our problems, because this is a problem, is you add the cut vertex. So here's our decomposition. So here's the original graph over here. Here's the tree over here that we're going to decompose it into two. So what we do is we take all the 2 vertex connected components plus all the cut vertices. Those become nodes. Then we take all the 2 vertex connected components plus and see if they're adjacent to some cut vertex. So notice that in this case here, these 2 vertex connected component are adjacent to that cut vertex, and so on. There's connections here. Each cut vertex is separating 2 vertex connected components, and they can be touching multiple of them, as you see in this hazard sign. So anytime that there's that connection, that's when we add an edge. Those become our edges. So let's see how this works on the hazard sign. Goes like this. Let's do the decomposition. What we get is a graph that looks something like this. So this node right here is the cut vertex right here on the left. And then each of these 2 connected components corresponds to a node like that. So that's our first one. You're always this graph is kind of neat. You're always going to alternate between having something that is a 2 vertex connected component and something that's an articulation point or a cut vertex. So you could have graphs like this. And then the articulation points are always going to be internal nodes. So just to clarify things, these will be the cut vertices. And these are all articulation these are all 2 vertex connected components. Something like that. So we could decompose any graph that we have into trees like this. Okay, so if we're dealing with the 2 vertex connected component, there's no point in us placing an escape tunnel here. The idea is if this articulation point went out, everything on this side of the cut could escape to a leaf over here. And everything from this side of the cut could escape to a leaf over here. So you can always get to the leaves when you cut any of these articulation points in this metagraph. That's the idea. So there's no reason to do the internal nodes, but all of the leaves themselves are necessary because if this articulation point does go out, everything in this 2 vertex connected component, everything in those edges, can only get to nodes in that component itself. So kind of a crazy problem in that regard. So you can't really escape those places. So you have to place an escape tunnel in every single one of these pendant nodes in the metagraph, and you only have to place them in the pendant nodes. So that gives us our answer. The answer is the number of pendants. And then we have to count the number of ways. That's also part of the problem. So what we can do is we can just take the product of num nodes in yeah. And this is for every pendant. So what I'm saying here is, let's say there were 2 nodes here, 3 nodes here, 5 nodes here, 6 nodes here, and you count the nodes that aren't articulation points in here, because that's where the articulation point lives. So just keep a count of how many nodes are in that subtree. Let's see if I can give an example. So for this tree, an example, those 3 nodes would go here. These 2 nodes would go here. So this would be 3 and 2. So I could hook an escape tunnel up to any of those 3 places. Those are our 3 choices. Or any of these 2 places. Those 2 are our 2 choices. And that gives us a number of ways. So if you think about this for a little bit, you'll realize that this algorithm doesn't work on every case. So we do have a special case we have to deal with on this problem. And that's the biconnected case. So the biconnected case is the graph has no articulation points, can't be cut. And so the idea is, let's say I drew my escape tunnel from that node, and then that junction goes out, then everyone can't escape because there's not somewhere else I can reach. So we also have to consider the fact that maybe the node that goes out is the articulation point itself. So in that case, you need at least 2 tunnels. And then the number of ways becomes just n choose 2. So that's how you handle that case. So something to keep in mind. So for this problem, I'd like to point out, you don't actually have to build this tree, this 2 vertex connected component tree. What you can do is you can find all the 2 vertex connected components using the technique in the last week's video, using a stack and doing a DFS. You can extract all those edges. Then you can search for each of those edge sets that you end up having, find out which articulation points each of those edge sets is next to. And it's fairly easy to check. It's just an if statement running through all of them. And if it's only next to 1 articulation point, then it's a pendant node. Same thing over here. This one's not a pendant node. It's next to 2 articulation points. So if you can check that, you can figure out which ones are pendant. You don't actually have to build the tree. You can just find the pendant nodes. And the same thing also exists for, I guess the last problem, you actually have to build the tree, but oh well. Okay. So that's problem 2. And so now time for the last problem. So this last problem is also a biconnected components problem, and it's called Lucky Cities. And I find this problem to be exceptionally beautiful. So this one doesn't involve tree decompositions. It's just a really nice biconnected components type problem. So stated fairly simply, if you're given a graph, what we want to do is we want to find all nodes that are on an odd cycle. So I'll give you an example here. So it's find so 1, 2, 3, something like that. And so you'll notice that these 3 nodes are on an odd cycle, and all the other nodes are not. So the answer here would just be spit out those 3 nodes. But you also notice if I add an edge here, then all the nodes would be involved in an odd cycle. So it's not that it's involved only in odd cycles. So maybe if I add something here, this would also count, even though there's an even length cycle. So it just has to be on some odd cycle, not only odd cycles. So the first thing I want to observe about this problem is the following. So the cycles cannot cross SCCs, or two vertex connected components. Right? So I have something like this. I can't have a cycle that involves both this node and this node over here. That's all I'm saying here. So you actually, if you decompose these into biconnected regions, then what you're left with, you can solve those problems independently. So the idea is just solve it for every two vertex connected component. The other observation is, so let's say I get rid of some things. Articulation points basically get to be in two of those decompositions. So if you are looking at the two vertex connected components and solving them independently, you're going to solve it once over here, keep that vertex, solve it once over here, keep that vertex. That's okay. You're only processing each edge once. And so the number of nodes is just 2 times the number of edges you process. So we're fine. At most 2 times the number of edges you process. So runtime is still going to be fairly good. Okay, so what we're going to do, we'll solve it for each 2 vertex connected component. So it's easier just to think of the graph as being biconnected. So let's talk about some properties of graphs related to cycle length. So we don't know a lot about what works on odd cycles, but we do know what works on even cycles. So if I have a graph like this, this is a bipartite graph. And so a graph is bipartite if you can divide it into 2 regions and nothing in those regions has an edge adjacent to each other. So saying a graph is bipartite is the same as saying it is 2-colorable. So the idea of saying 2-colorable is you give each of these nodes a color such that no edge is between 2 nodes of the same color. And so you only need 2 colors if a graph is 2-colorable to color the graph that way. And that's the same as saying there are no odd cycles, or only even cycles. And the reason for this is if you start on one side of this bipartite graph, if you have a cycle, you have to finish on that same side of the graph to get to the same node. And you'll notice it takes an even parity number of steps because you go left and right and left and right. So it's going to take an even number of steps in all cases. So all the graphs are even cycles. All right. But this is the only time this odd cycle has come up. So if you play around with things a little bit more, let's take a look at a graph here. If I look at a biconnected graph, there may be a node like this node that's part of an even cycle. You might conjecture pretty quickly that, hey, wait, I can turn that into an odd length cycle. And then you might say, can I always do this? So here's my conjecture. If a 2 vertex connected component is not bipartite, or it's not 2-colorable, in other words, then the thing I would think I can conclude is all nodes are on some odd cycle. So that's the conjecture. So what we're going to do is I'm going to prove it. The proof's pretty simple, actually. So if we know the graph is not bipartite, then we know it has at least one odd cycle. Doesn't mean all of the cycles are odd, just know it has at least one. So what we're going to do is we're going to do something like that, maybe something like that. So that's the cycle that I have here. Okay, so what we need to be able to do is we know this cycle exists somewhere in our component. We also know that there's some vertex that we want to put on the cycle. So we want to put it on the cycle somehow by taking where the cycle is currently and then adding it to the cycle. And if it's not on the cycle, then there's a problem. So what we're going to do is we're going to just take two vertices that are on the graph, and we're going to look for a path to that node and a path to this node. Something weird could happen. It may have to go through this edge, and in which case we just change it to use this node, right? So what I'm going to do is I'll just pick those two nodes. And so they have to exist. They're not going to overlap the cycle in any way. We have two paths coming off of this. So that's our graph. That's our vertex. So I'm just hooking it up to the odd cycle. Now, I know that this path has some length. I'll call that L1. This path is L2, has some length. L1 plus L2. I'm going to call that V. Don't know why. Maybe M. I'll call that M. So M is either even or odd. So it's either congruent to 1 mod 2 or 0 mod 2. But it's basically either odd or even in length. So I want to make this on an odd cycle. Here's a cool part. This path over here, there's going to be one side that's even or odd. There's going to be one side that's odd. Yeah, let me use blue. There's going to be one side that's odd over here and one side that's even, because this is an odd length cycle. So in order to make it odd, I'm decomposing it into two amounts because I have two different vertices here. One's going to be odd, one's going to be even. And that's the only way we can form an odd number. You can't form an odd number by adding two odd numbers or adding two even numbers. So what we do strategically is we look at M. If M is even, then we make the cycle take everything plus the odd piece, and now it's an odd cycle. And then we look at M, which is these two, and if it's an even piece, then we hook it up like this, and we make an odd cycle. So in either case, we can make an odd cycle for this vertex using this constructive method. So thus, any vertex in a two vertex connected component is on an odd cycle. Pretty simple. Yeah, non-trivial conjecture, but hopefully you enjoy that proof. Let me know if you have any questions about it in the comments. So I'm keeping things a bit arbitrary here, and that's what's keeping this proof okay. Okay, so now we're left with the solution to the problem. So the way the solution works is you construct all the two vertex connected components using DFS lowlink that we went over in the last video. We get all of those. For every two vertex connected component, we try two coloring it. If it's not too colorable, then all those vertices are part of an odd cycle. They have to be. And then I just mark those vertices and then print them all out at the end. And so I have to do it once, maybe multiple times for cut vertices. That's all you have to do to solve the problem. So definitely give that one a try. It's a lot of fun to code, and maybe code a bunch of these. These are, I think DFS low-link problems are just really fun in general. They're fun to reason about. You get to do some tree decompositions, and the algorithm itself for like finding these components, I just find to be really simple but really cool. So thanks for tuning in this week. See you guys next week. I'm going to, in the next episode, I'm going to cover strongly connected components. So we're going to look at this low linking technique again, but we're going to look at it in the context of directed graphs and see what we can figure out on directed graphs. So see you all next week. Can't wait.